Hello everyone. So in this video we will begin with chapter 6, Modeling Real-Life Phenomena. So let's talk about the learning objectives. By the end of this chapter you should be familiar with modeling linear piecewise, quadratic, cubic, exponential, direct or inverse variation, and trigonometric phenomena. Developing and fitting models, recognizing the context, choosing an appropriate model, determining a reasonable domain and range, and using technology to find parameters. Testing and reflecting upon models, commenting on appropriateness and reasonableness of a model, justifying the choice of a model. And finally, using models, reading, interpreting, and making predictions, avoiding extrapolation. So we begin with section 6.1, linear models. So linear models are used to describe situations where one quantity, the dependent variable, increases at a fixed rate relative to another quantity, the independent variable. So obviously we use linear functions to model these situations. So let's take a look at example 6.1. The I&T Fitness Center charges a one-time joining fee of $100 and then charges $2 per visit. Part A, develop a model for the total cost after V visits. So we can say that the total cost is going to equal the initial fee of 100 plus $2 per visit. So this would be a simple linear model of this situation. Then it says in part B, use your model to find the cost of 20 visits. So the cost would equal 100 plus 2 times 20, and this is going to be $140. That would be the cost after 20 visits or of 20 visits. Draw a graph of your model in part C. So if we draw the graph, this is what it would look like. Notice that it starts at 100, which is the initial fee, and then it increases at a constant rate of $2 per visit, as we can see here. So 0, 100 is the y-intercept, or in this case, the c-intercept, because this y-axis represents cost. And then on the x-axis, we have the number of visits. So notice that by 20 visits, the cost is $140. So you can see that the cost increases at a fixed rate relative to the independent variable, which is the number of visits. So next we have example 6.2, and it says, a visitor to the I&T Fitness Center decides not to buy a membership and instead just pays the daily rate. The first visit costs her $12. At the end of the month, she notices that she has visited 5 more times and paid a total of $60 for those 5 visits. Part A, develop a linear model for the total cost after V visits. So it looks like the cost per visit is $12 because if we divide 60 by 5, this also equals 12. So that means that she's paying $12 per visit. In other words, the linear model would simply be C is equal to 12 times V, or $12 per visit. For part B, use your model to predict the cost of 20 visits. That would simply be C is equal to 12 times 20, and this is going to be $240. So this is a bit more expensive than the previous example, right? Where the rate was $2 per visit plus the fixed rate or the initial amount to pay, which was $100, and it gave us 140. So this is a lot more, right? $100 more. For part C, it says, after how many visits is it better to buy the membership described in example 6.1? So in example 6.1, the model was C equals 100 plus 2 times V. So we need to compare it with this model. Basically, we equal them. So 100 plus 2V is equal to 12V, and we solve for the number of visits that would tell us when they are the same. And notice that this is simply going to be 100 is equal to 10V. So that means that V is equal to 10. So after 10 visits, it's probably going to be better to use the previous model, the membership model. Now let's take a look at this in a graph. So in blue, you can see the model for example 6.1. And although you start paying $100, the rate at which it increases is slower than obviously paying $12 per visit. Although it starts cheaper at first, but then after 10 visits, the costs go up quite more, right? Because the rate is $12 per visit, whereas here the rate is $2 per visit. So this is the point at which it is better to have a fixed membership. So we continue with interpreting and evaluating linear models. It is important to be able to recognize the structure of a linear model and interpret its meaning. Also, we must be careful to recognize limitations of linear models. So let's take a look at example 6.3. And it says, the number of items that a clothing store sells can be modeled by the function n equals 1000 minus 5p, where n is the number of items sold and p is the price of jeans in euros. Part A, use the model to predict the number of jeans sold when the jeans are priced at 100 euros. So we have that n is going to equal 1000 minus 5 times 100. And this is just going to be 1000 minus 500. So that means 500 jeans. So in other words, if the price of the jeans is 100 euros, then 500 jeans will be sold. For part B, it says, interpret the value of the gradient and the n-intercept in context. So if we imagine a graph for this case, let's just draw a couple of lines here. N is the dependent variable, so we write it on the y-axis, and then P is the price. We write that on the x-axis. So notice that at the beginning, you would sell, or the store would sell 1,000 items. So let's say this is 1,000. And then gradually, because this is a negative number, it means that this line would be decreasing, right? At a slow rate, but just for the sake of interpretation, we're going to do this way until it reaches a value of 0. So the gradient means that because it's negative, minus 5p, it means that the more expensive the jeans, the less that will be sold, right? And then the n-intercept, which is this here, right? When p is 0, when p is 0, n is 1,000. So it means that if the jeans are free, they cost 0 euros, then 1,000 will be sold. So this is not very logical, and that's a limitation of this linear model. For part C, it says, interpret the value of the p-intercept in context. So the p-intercept would be this here, this point. So that means that n would be 0. So that means that we need to find the value of p that would make n equal to 0. So we say 0 is equal to 1,000 minus 5 times p. So notice that if we solve this, we are going to get that p is equal to 200. So that means that here this would be 200. So if the price is 200 euros, then no jeans would be sold. That's what that means in this case. For D, it says, use the model to predict the number of jeans sold when the jeans are priced at 500 euros. Give a reason why this prediction is not reasonable. So the number of jeans sold when the price is 500 would be 1,000 minus 5 times 500. And notice that this is going to give us a negative number, right? Because 5 times 500 is 2,500. So we end up with a negative number of 1,500. So minus 1,500 jeans. So this is not reasonable because there's no way you can sell a negative amount of jeans. So we continue with piecewise linear models. Sometimes a real-life situation is not modeled by a single linear function, but is linear in parts. Consider the following example, and it's example 6.4. And it says, a phone company charges a rate of 24 cents, in this case, or $0.24 for the first minute of a call, then $0.12 per minute for the next 9 minutes, then $0.06 per minute thereafter. Calls are charged on a per second basis. Part A. Develop a piecewise linear model for the cost C of a call lasting T seconds. So these piecewise functions or models look like this. You would go, okay, so C is equal to, you write a bracket, and then within this bracket, you're going to have, in this case, 3 different linear functions. So first notice that the company charges $0.24 for the first minute of a call. So if we go 0.24 divided by 60, that's going to give us the rate per second. And if we do this, this is going to give us 0.004. So that means $0.004 per second. So in the piecewise function, we would write 0.004 times t, and this is for t greater than 0, but less than or equal to 60 seconds. Now, for the next 9 minutes, it says that the charge is 12 cents per minute or $0.12 per minute. So that means that we would have to divide 0.12 by 60, and this is going to give us the cost per second. So this is going to be 0.002. So $0.002 per second. Now for this second linear function that is part of the piecewise function, we have to consider the cost that is accumulated for this first minute. So that's 0.24. So it starts at 0.24 and then plus the new rate that we found, which is 0.002 times t minus 60, because this is going to be for time after 60 seconds. But the time is going to be limited here because it says it's only for the next 9 minutes. So it's going to be from 60 up until 600, which is 10 minutes, right? Because 1 minute here and then 9 more minutes would be a total of 10 minutes, and 10 times 60 is 600 seconds. Okay, so for the next one, we have to also take into account the rate. Now it's going to be 0.06 per minute. So we have to go 0.06 divided by 60, and this is going to give us 0.001. So this is the cost per second. Now, like we did in the previous one, we have to take into account the accumulated cost, and that's going to be for t equals 600. Because if we put in 600, t equals 600, we're going to get all the accumulated cost up to this point. So if you plug in 600 here for t and subtract 60 multiplied by 0.002 plus the 0.24 accumulated, you're going to get 1.32. So we have to start off at 1.32, which would consider all the previous time. And then plus the rate, 0.001 times t minus, now in this case, remember that t would have accumulated 600, so it's got to be over 600. So t minus 600. And this is going to be for time greater than 600 because it says per minute thereafter. So this is going to be the cost after 600 seconds or 10 minutes. So this would be the piecewise function that models this real life situation. For part B, it says use your model to calculate the cost of calls lasting 45 seconds. So for 45 seconds, we have to pick the first function, right? So it would simply be 0.004 times 45. And this is going to give us $0.18, right? Or 18 cents. For part 2, they want us to calculate the cost of a call lasting 4 minutes. Now, 4 minutes is 240 seconds. 240 seconds would fall into the second category, or into this function, right? So we would say 0.24 plus 0.002 times 240 minus 60. And if we plug this into the calculator, it's going to give us $0.60 or 60 cents. And then for number 3, I'm going to do it up here. For number 3, we have what is the cost of a call lasting 15 minutes. So 15 times 60 is 900 seconds, right? 900. So that would go into the last function in this piecewise function. So it's going to be 1.32 plus 0.001 times 900 minus 600, so that's 300. Plug this into the calculator, and it's going to give us $1.62. So if we were to graph this piecewise function in the GDC, you would notice that you have 3 different functions in one. Notice that from 0 to 60, we have this part here where the rate is increasing faster, right? Because the cost is higher. Then from 60 to 600 seconds, you would have this other line up to here. And then after 600 seconds, we would have this other line. As the number of minutes increases, the gradient of the line decreases because the cost is going down. Although after this point, the cost would continue being the same, so this line would continue indefinitely in this direction.